So hopefully you enjoyed the last video with this collapse of a gas cloud and starting formation of protostars starts. That it's not only one, that there is always a large number born. Of course, now we ask ourselves, where are the siblings of our sun? The Keplers, this happened 5 billion years ago. And since then, in a relatively chaotic system like our Milky Way, we have no clue where this happened. And we have no clue what are the siblings. So our sun lost its family. We have seen this, and we have seen this rotation, and it looked this like. And another thing what I forgot to tell you is about the dimensions. If you look on, take another look, then you see something with 80,000 whatever AU, astronomical units. 80,000 times the distance from Earth to Sun. If you remember, the distance towards our nearby star was a couple of 10,000 of astronomical unit. Yet this is still a relatively small gas cloud. There are bigger ones, far bigger ones. So massive amounts of interstellar gas, quite big dimensions, which is enough to form multiple of gases. Not of gases, of course, of stars or protostar systems. So let us go step through step and clarify a few of these mechanisms. And one mechanism that we encounter is that we will have this flat disk. A flat disk, where does this come from? And very likely we get jets perpendicular towards this plane of this disk. There will be material will be ejected. So formation of these disk-like structures, you probably already know that galaxies also mostly are disks, most of them, or not most of them, but the original version of them. So why always disks? And then the second stuff will be why these jets? These two mechanisms, and they will be not found only now, they will also be encountered later in other systems. So we basically start from dust to star with a gas cloud, and here this is now 200,000 astronomical units. So, quite a couple of light years, so 20, 30, 40 light years, so quite something in diameter. Then we have this dense cores. Where does this denser cores come from? Well, where do they come from? Obviously, first generation stars. This was this accumulation of dark matter clumps that then accumulated also via gravity a bit more visible matter. And from there, we get this structure formation and probably also then our first stars. What is nowadays often is that there nearby might have been a cataclysmic event which sent shock waves. And then you have obviously waves that are where you have already denser points hitting another dense point that might start to originate and this further structure formation. So often you need some cataclysmic event nearby, like a supernova where a star explodes, or something that makes the gas a bit more moving. So then obviously you have a seed And the seed attracts more and more matter. And the more you have, the more stronger gravity, the more is again like a vacuum that is now sucking everything from nearby towards it. We basically get this gravitational collapse with the local cloud is about 10,000 astronomical units. At the time t equals 0, so the starting point. So what forms then? We have seen these disks. So the disks, still stuff is falling in. So we talk now about 500 astronomical units contracted by a factor of 20. Then talk about the protostar. In the center, we have here this disk of material and a bit of an envelope. And seemingly what forms then out are these jets. What brings us to the question, why these accretion disks and what causes the jets? Well, look again back our original gas cloud with this hundreds of thousands of astronomical units. It means a few light years. It might already have some sense of rotation that it somehow rotates and while it starts contracting. And now when it contracts, it starts to spin faster. So, and the more and more it contracts, the faster it seems to spin. And when this spinning happens, there seems to, in this original plane where the spinning perpendicular to the spin orientation, there builds it up this disk. So the rest could contract somehow towards the center, but not in this disk. What is the responsible? And then we are back to a quantity we have encountered with Kepler's law, the angular momentum. The angular momentum is mathematically defined as, well, this here m times v. This is just should be a dot. That's the linear momentum, which describes the state of motion of a body of the mass m with given velocity. Same velocity, different masses results in different momentums. But equal momentums doesn't mean equal velocities, because there is also still the mass involved. Now, if we have some kind of rotational movement, we have here a radius, and often they are perpendicular, the radius and the momentum. Well, what we usually get is that the cross product, the vector cross product, defines as a third vector, which is perpendicular on the plane defined by r and p. And this vector, which can also be written r times mv, or the mass can be taken in front of because it's a scalar quantity, it's just a number. This is our angular momentum. This can be also defined as I, where this is what is called the moment of inertia, the mass distribution relative towards a given rotational axis, which would be here identical to L. So this is the same direction, this omega, that's the same direction. It's the angular velocity, or the angle, how fast it's basically changing with time, how quick is it rotating. Instead of considering the mass point out here, we're considering the angle. And how is the mass distributed relative towards this rotational axis. We have seen this in Kepler's law. Here nearby, obviously from the furthest away point, in order to come closer and closer and closer, we get an acceleration because it's now closer. It has been somehow attracted by the gravitational force. What means the velocity increases, which is then shown by the length of this vector. Or this arrow that represents this vector quantity velocity. So then obviously in the same times, the same the product of this radius and the momentum is the same, stays constant, but now v is larger, but in the same amount r has decreased. So the product stays the same, the area that is in here is the same. That was Kepler's second law, where we encountered this already. That would be basically this upper description. And now the lower description is this moment of inertia. And omega, well, so this angular momentum conservation, but now we have here the second one, which is relevant for us for the contracting gas cloud, where obviously the matter distribution towards this rotational axis that is perpendicular is changing. It's contracting. Okay. The system is contracting, but the entire quantity is preserved. So we change now r squared, r, therefore r squared is shrinking. What has to increase? So if this is I corresponds to the mass multiplied with r squared is shrinking, means this omega has to drastically increase. This angular, it has to spin faster and faster and faster and faster. The classical example, which is not entirely correct, but it nicely shows the effect, is the figure skater. This lady that is now figure skating. So the arms out. The mass distribution is r squared, is large relative towards the rotational axis that is obviously perpendicular to the body, the symmetry axis of the body. But now the lady takes in the arms and shrinks this r squared drastically. What happens? Her rotational velocity becomes, this angular velocity becomes much, 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 much faster. Then when she takes the arms out, she slows down again. So this is the same effect. And the preserved quantity is this angular momentum. So angular momentum is a preserved quantity in a closed system. This has also as consequence, well, the stuff that is here perpendicular on top, it doesn't feel this angular momentum. It can nicely fall into. That is fine. That it basically it falls into, accumulates the center. Yet the stuff that has an angular momentum can fall into this disk, attracted by already some gas that is there, or some gravitation, enhanced gravity. But once it's in this disk, it has a problem because the gas molecule cannot migrate towards the inside. If it migrates towards the inside, it becomes faster. But if it's fast, it's overshoot. So it's basically bound on some of these Kepler ellipses. What a crap. So we get this disk formation thanks to this angular momentum preservation for the material that is not perpendicular or close to perpendicular. How can it be that our sun still has 99.99% of the mass in the solar system? And not just the cylinder that is above it. And the rest falls in here. Well, we have a fluid, or we have the atoms and molecules in this accretion disk. And now we have a collision. In a collision, usually one partner loses a bit of energy and the other one gains. So at the moment, we can't fall in the disk form directly. And we have this nice picture as shown here. But now we need also a mechanism where stuff still can migrate towards the inside and stuff can migrate towards the outside and get lost. So, but we have this disk as explained thanks to angular momentum conservation, because the stuff above and below can nicely fall into the center, but not the stuff in the disk. And obviously the rotational sense must be on perpendicular towards this axis. This is the photograph we have seen at the beginning, and this is basically when the protostar, the star before the star, starts to form, which is hot because now we have a lot of gas that was previously nicely distributed, concentrated in a smaller area, where basically it's like when you have a pump up your bicycle tire, you take the pump, you press air together. What happens with the pump? If you do it often enough, it gets warm. It's not explained by the common this ideal gas equation. We need the what is called the van der Waals equation for real gas, which has interaction between the molecules and that stuff. But what happens? The gas gets warm because you compress it. The same happens in the star. Density increases. In the center, you get it hotter and hotter. Also something very important. Well, in general, what the gas would like to do is, of course, to expand again. But the gravity keeps it together. And the gravity is strong enough to overcome this thermal movement of the gas particles and binds them now together. So, but all that works not to have a complete collapse is the angular momentum conservation that builds up this disk. And of course, the thermal movement is important. Otherwise, the star would immediately collapse and the gas molecules come closer and closer and closer and closer until we might overcome a certain limit and form a black hole directly. So we have this contraction, but now what's going there on? Well, and then here in this disk, what do we have already here? What would you say? What is rings of this lack of material? Where does this come from? Oh, that's to say there must be already protoplanets forming while the star is not even shining. They are basically stuff that collects already the material and forms clumps of material that then have already this angular momentum from the gas molecules and start orbiting around planets. And remember the definition of a planet? That it has cleared its orbit. The difference between a dwarf planet and a planet, that it has cleared its orbit. And here it becomes relatively clear. And one sees even almost the size of these planets. here must be something smaller, there is something bigger, here's obviously something really big, here's something really big. That clears already quite a lot. So here now this definition makes sense. It has cleared its orbit. Not of the last dust grain or something, but at least most of the stuff is gone. So here obviously we have the reformation of planets also. Fantastic photograph. And we have explained why we have these discs-like shapes. Because of angular momentum conservation. Of course, there is still gas that can migrate towards the inside because of collisions. One loses energy, velocity, and goes a bit more to the inside, and the other gains and goes a bit to the outside. So occasionally there is stuff migrating towards the inside and stuff is migrating also to the outside. Yet we want also to explain why occasionally this phenomena of jets comes along. So we have already explained accretion disks. We'll later talk about galaxies. What will be the reason why we observe disks? Angular momentum conservation. The original gas cloud was somehow slowly rotating, and it might be only just locally, and then locally we form from this big cloud locally basically a galaxy. Oh, which is disk shaped. Later on we're going to see a video of a black hole feasting on a star that came too close. It rips the star apart, and then the material cannot fall directly in because there was already a velocity component bit perpendicular. So perpendicular to the radius. Angular momentum is there. The stuff needs to rotate around, and in collision, some stuff is lucky and gets a bit higher velocity and might escape, and the other stuff has bad luck. Well, loses angular momentum and at some point is eaten. And now comes the second mechanism that happens then. Obviously, if stuff is getting also faster, the stuff that is in the inside needs to rotate fast. You have a relatively dense. This means it's hot. The central region is hot. The gas is becoming ionized. Also, in the accretion disk, the center becomes very hot and the gas will be already ionized. That means collision. Electrons are kicked away from the atoms. You have an ion, you have an electron. Now you have moving charges that are basically in the circular movement around this center. You have a current. So every moving charge corresponds to a current. Here you have a ring current. A current causes a magnetic field. This is simply one of Maxwell's laws. So every time you have a floating charge, this corresponds to current, and then you get a magnetic field. That's induction law. Okay, and now if you have a ring current, you get a nice magnetic field. So this would basically, this I is the inner ionized gas that we have. Electrons and ions. They float around and form this ring current. And now you get around the current, you get in concentric circles this magnetic field, whose strength decreases with the distance. In fact, one with over r squared, or 1 over the distance squared, the strength decreases. So we would not, if this would be just a line, there would be nice circles around. Now in this ring current, what we get is basically each magnetic field lines are always closed. There are no magnetic monopoles, like electric monopoles, a charge, positive charge, and then from there you get perpendicular to the surface going out the electric field. Magnetic field is always closed loops. If you find a magnetic monopole, you get Nobel Prize, probably 5 Nobel Prize at once, and you get the title of revolutionizer of physics. So what we have is, of course, on the inside, the field lines from everywhere cram each other. So if we just take 2 points, one here, then we see the field lines, and obviously they cram each other in the inside, and on the outside there are less dense. So the number of lines going through an area perpendicular to them is obviously here much denser than here. It means here the magnetic field is much stronger than out here. So on the one side, we have now these charged particles that create this current. Yet we have then other charged particles that might be now trapped in this field line, that are not moving in this ring, but are coming from perpendicular, that somehow collide charged particles. So what means an ion is created, an electron is created. And what happens is now Lorentz force. It's called Lorentz force. It's a force that a charged particle experiences in a magnetic field. So there's a feedback loop. So these charged particles, they are often then trapped because they are moving perpendicular towards or in a circle around this field line. Okay, so they are trapped. If they have originally the movement towards the center, what happens? Well, they would gyrate around this field line towards the center. Now, charged particles basically want to be in a region where the density of field line is minimized. This corresponds to an energy is given by what is called the magnetic moment, which is somehow the magnetic charge of a charged particle. So the strength, how strong it couples to the magnetic field, multiplied with the strength of the magnetic field. Nature wants to minimize this energy. So the magnetic charge, that's a particle property that is not going to change. But the field strength can change. Where does the field strength is less? We just discussed this. Inside, we basically have it very strong, and outside, we have it relatively weak. So a charged particle always wants to travel towards a region where the field density is low. What means if it's once here, it gets usually accelerate towards the outside. And at some point, it might be so fast that the Lorentz force is no longer strong enough to hold it, and it gets catapulted away. And obviously, particles that are trapped here with a certain velocity that travel here, at some point they will stop, and then they are accelerated out again. And it might happen so fast because the magnetic field strengths in here are so strong that they overshoot, therefore are blasted into space perpendicular to the ring current. That means the accretion disk that created the magnetic field. This would create us these jets. That's the so-called dynamo mechanism. Oh, I know this was now loads of physics. So first we ionize basically the gas that is floating around in the accretion disk. This forms as a current. This current creates this magnetic field lines in circles around it. And if a particle is coming there, it's trapped by one of these field lines and then accelerated to the region with lowest field line density. What means somewhere outside, what means away from the center again. In the moment, we have basically, it's so hot that we can ionize. It's hard to fall more material inside, at least perpendicular. This is then happening obviously in later stages. But we get this dynamo mechanism. So basically, once a particle is trapped in here, it gets accelerated out. And very likely it's already in a very narrow range that it's so high in energy that it can be blasted away. So we form these jets. That will last, of course, until the material is used away. And the next, so this would be now in 100 astronomical units, typical size of a solar system. I remember the distant sun towards Uranus, Neptune, this was 30, 40 astronomical units, and then 100. This was about this Kuiper belt, this loose material that is somehow surrounding our solar system in a ring. But for any strange reason, this ring is twisted by, I think, 7 or 8 degrees towards the rest of the plane where the planets are going in. By the way, we have now nicely explained why all our planets, except of Pluto, but Pluto is just a dwarf, are nicely in one plane. There's this accretion disk that formed in the very young solar system. We get a disk, and in this disk, local density instabilities start to accumulate by moving around and grabbing more and more of this gas and forming planets. But then you have something that inside, obviously, it's hot. It's methane gas also might be so hot that it goes away, while silicate, silicium oxide, that might already start clustering because its melting point is lower. You form in the center, or towards the center, more silicate planets, and when you go outside where it's cooler, the methane or other gas might already be capable to cluster together. Yeah. So basically, from this disk, this debris, the planets form. And at some point, 100 astronomical, now our solar system, 50 astronomical units. Well, what happens? There are then two other effects we're going to talk about when we talk about how our solar system originated. How is the structure of our solar system to be explained? Because at some point, Jupiter and Saturn even went inside and then they went outside again. And on this move inside, outside, they collected loads of material. How can they migrate inside? Only if they give away somehow angular momentum. That means the radius will shrink. How can they move outside? By gaining angular momentum, by collecting something and then making the mass bigger. gain angular momentum and move outside. We're going to talk about this. But obviously, we have now nicely explained why we have all the planets in this stuff. But what here we still have gas, and here, well, is this all collected, or what happens? Once the star shines, starts producing energy by itself, it settles so down in the center, it starts producing energy, it starts producing light, and this light slowly but surely goes to the surface. In fact, in the center it produces very hard light, and on the surface it's rather soft light. It's very hard light, what means gamma rays harder than X-rays. This is transformed in multiple scattering processes towards the surface, and the surface, what comes away is most heat radiation, because the body is so hot, but it's heated from the center. It must be, because otherwise if you have a hot body, what does it do? It cools down. Even if you have it in vacuum, it cools down because it irradiates this light, this Planck light. It gives away some energy. This must come from them. This is the heat that shrinks. So we need now a heat source that keeps the star the same temperature all the time. What is irradiated must be produced. At some point this happens. And then we have said that this is at the young star, not everything is settled down. It emits a lot of UV light, and now comes into game that light has a pressure. You have these gas molecules around, but now suddenly you have a light source, relatively intense compared to what was there before. Just this heat radiation, forget about. Or this heat radiation of the hot gas, forget about, compared to the other heating source that is then active. You get all these little photons, and photons, light particles, they have a momentum. If they have a momentum, momentum is the change of force with time. So if we integrate over time, this is a force. And they push now the gas molecules towards the outside. And basically, slightly but surely, they clear also this gas away that is still here at the protostar before the star ignites. And once it's ignited, it produces photons and they wipe out this gas away. And of course, at some point, this gas might start to cluster together again and form ice clumps or methane clumps or comets. So again, we explain why we have all this debris out here, called the Kuiper belt. And now, in order to get it twisted, there must have at some point a body past the solar system, which tracked the outer one a bit more stronger in one direction. So when the sun was relatively young, there must have been one of the siblings or maybe another one, next generation star or whatever, passed by in relative close distance. Oh. But we also explain now, the star forming regions, like for example here, near Cassiopeia. Don't know how this is now called. I should have noted this down and forget them too easily. So if you look in the night sky, and then relatively central at the moment, so bad for the neck, of course. So, and I wouldn't recommend you at the moment to lie on the ground to have a better view up. Too cold. You find this W. That's Cassiopeia. And on one side of W, you find then another nebula. And if you look again in this nebula, here it's again optical. What we find then is again regions where loads of stars are created at the moment. By the way, if you look galactically, we have these spiral arms in the Milky Way, and they rotate. And this is usually at this nebula often found at the front side of these rotating galactic arms. Of course, they collect the dust that is there around, and then you get some kind of bow shocks. You accumulate a bit of dust. And of course, if you go to the center of the galaxy, there you find more dust than on the outside. In fact, the galaxy often loses gas towards in the plane. That's collisions. One loses angular momentum. Farewell. This is then often recycled via a circle perpendicular to the center coming in. If a galaxy is without dust, what will happen? Star formation will cease. No more new stars are born. That means the ones that are there have a certain lifetime and they have burned away their fuel. That's it. So sad to hear about galaxies that with time they lose their gas. Therefore, star formation will stop at some point. But in the Milky Way, it's still quite ongoing. And when you remember the merger Milky Way to Andromeda, when this happens, there will be often that regions of critical gas density will be created. This will be a party of star formation. Born, plenty of stars will be born, but this is probably the end, because in this process, when the center of gravity stands, guess what is lost? The light stuff, the one that is easily, or it's just moving away because it's not so attracted by gravity, by this common center of the dancing. So this will be the last highlight of star formation, very likely for this common galaxy that forms. I know it's a bit sad, but it happens in a couple of billion years. So until then, we're going to see what's happening. So, but we also have seen basically at this very simulation at the beginning, stars often form in a narrow region. What means they have on the one side the chance to trap each other in their common gravity, gravitational potential, basically trap each other and form binaries, triplet, quartet system. If you think back, there's this, I think it's Tatooine and Star Wars, where you have the two stars at once up. So there are often that we have star systems with multiple stars, which then rotate around. But for life, this is not a nice project or prospect. Why? When you have these two dynamical centers of gravity, we don't care about the gravitational waves. The bodies are too far away, they are too light to really significantly at the moment to irradiate energy via gravitational waves. No, this is not the reason. But try to make a stable orbit for a planet with just the right distance to be away from the star, that you can have water in liquid form, or water, H2O in liquid form. If it's too close, you have water vapor. If you are too far away, you have solid water, what means ice. And the chemical reactions to create life, you need water in liquid form. So there is this narrow band, and if you have 2 stars and a planet around, poor planet, it will be not, there will be a period, it comes too close to one, and then all the water is evaporated, and it might be a bit too far away, and all the water vapor is condensing, and then forms ice, and every time everything is evaporated, the escape velocity for the water is quite high. So this planet is sooner or later losing its water. So in binaries, it's very unlikely, in tertiary even more, and to find that the conditions that their life would evolve. Again, we are quite lucky that our sun didn't find a sibling to form a binary. So this is quite common, and there were assumptions that 70% of the star systems are binaries, but some are so 60 to 70% maybe in the Milky Way, but this is now again under scrutiny. So it's again strongly discussed, and people say this number is far too high. Yet there are quite some. Another mechanism, except of this trapping, then when they have been formed, is of course that can happen when the original cloud collapses, that we have a neck. And this neck splits in 2 centers. But these 2 centers are then still trapped by a common center, or if you make the superposition, there will be still a common center where they both rotate around. And we get then in the end a binary system. So this is also possible. And here's a photograph from some colleagues from Japan. Unfortunately, I should have, when I made the slides, I was quite in a hurry to get some lecture course together, and then it's bad practice. I should have given here the source where I took this photograph. What you see is basically a binary system of 2 very close line ones. And you see they are so close line, they even exchange no material. So the big one is nicking from the small one. Big one, it's heavier, therefore the gravity is stronger. So then around there seems to be another disk of gas. So seemingly this is now already or just a binary that just formed. But how can we recognize that we have binaries? Because often then if they are distant sun to Earth or astronomical unit away from each other, can we resolve this? Well, maybe in the neighborhood that we see there the 2 dots, but to resolve this in a photograph or in a picture, latest when it's a bit away from us, will be hard to do. So what will be the way to detect that we have binaries? And I think, the good thing is, sorry, this video is now getting again too long. Yet we are coming close. So what is the giveaway? Well, if we have one star that is brighter and the other is a bit dimmer because it's smaller, and then according to Planck, the surface area is smaller, the spectral radiance, the luminosity is smaller. its temperature is anyways more lower, so we even get a different Planck spectrum. But if you just look at the total amount of light that is coming, and now if the dimmer one is moving basically in front of, would be here, if we look from here, they're next to each other, it's the super brightness because we get the light from both stars. But now the dimmer one is moving in front of the other, that means it blocks away the light. We get a decrease in the brightness. This is of course happening as long as this one is passing in front of. And then once they're next to each other, we see this again. And then when the dimmer one is moving behind the other one, so this here, we can't see the light of this one. Again, the system is dimming down. So, what means periodically we will see a change in light or in the brightness of these stars. But of course, this must happen that our line of sight is just in the right line from this plane where they must be in the plane where they orbit. If you look from perpendicular, so basically like we look now on this slide, will be always the same brightness. So it's already there something that, of course, if we look from a different angle, we might have just this part partially, but there's a certain angle where we always will see both stars. Yet we can roughly estimate from the ones that we see and then how many must be in total. And here again, this Gaia data will be very, very useful. Do you remember Gaia? This stuff that maps our quarter of the galaxy. And does so regularly 60, 70 times per star. So there it might be also very useful to check out how many binaries are really there. Or is this the 60, 70%? Or is it less? And binaries, well, so the typical giveaway we see it's the light curve. But it's relatively easy to measure. By the way, nowadays we use the same effect, but there is not a second star that is passing in front of. Nowadays we use the same effect for planets. And you can imagine when we are down to the Earth-like planets, our sun, and then the Earth moves in front, and you watch basically from 100 light years, 200 light years away. And you see a per mil of the surfaces is then 1/1000 of the surface of the sun is blocked away. 1/1000 of the light is missing. In a very, very bright object. This is if you look into a torch and the fly flows, you often can't see it because it's anywhere you're flagged. But nowadays, the CCD cameras, they're sufficiently sensitive to this 1/1000 change of light, bit dimmer, to recognize this. And then we can see there's a planet. And then from basically in the total, how much it blocks away of the light, we see the relatively surface. If we know the surface of the star from Planck's law, for example, we know the temperature, we know the surface, if we know the distance, so we know the brightness, you see how things nicely form. And if we now know how much is blocked away, we can go back for the size of the planet. Then we see how long this is here going. We know the orbital period. So we are getting information together about star system. And in the very last lecture, I'm going to tell you how we might be able to figure out whether there are plants on the planet, or even how we might be able to figure out whether there is a technological civilization on this planet. It's unbelievable that we are so sensitive in our measurements already. But for binaries, what I want to tell you, stars are created in the same region, and it's likely that we form binaries. In fact, sometimes this Astro-Gemini system, for example, Betelgeuse, bottom right, this bluish star, Rigel, 4 stars. And quite remarkable is this Astro-Gemini. This seems to be a star system with 6 stars. So very complex movement inside the star system. So all around one common center of gravity, but obviously the two bigger ones are the dictators. So these two are obviously the dictators, and the other ones probably are going on very unstable orbits around them. So, well, what we haven't answered yet, what makes the star shine? So, protostar to star. Where's the difference? Why does it suddenly produce so much energy? That it's not only hot, and therefore we have this thermal energy, and we need ALMA, or large millimeter, submillimeter array, to get the heat radiation. Why do we at some point get so much light in the visible range? Where does this energy come from? Well, this is here like a series, so you've got to wait another week. But I think it's now enough. You have now 2 hours, or roughly more than 2 hours, very likely, just about the birth of stars. And it's very important, the importance of angular momentum and induction. Okay, then see you next week.